Good morning, good afternoon, or good evening. This is now the final question of the Step 2 2024 paper, our final stats question. As always, you should only be watching this video if you've already had a strong attempt at the question itself, and you've either completed it and you want another viewpoint, another way of tackling it, or you've got stuck and you're looking for a small hint. As always, if you have got a hint, you should then pause the video, go and attempt to use it yourself before carrying on and watching the rest of the solution. We are on the final question of the paper, so hopefully this playlist has been helpful all the way through, and we're going to tackle question 12. Very similar to the previous stats question that we did, we're starting with what seems to be a pure idea. We've been given the two summations for the sum of the squares and the sum of the cubes. Again, very worth as you go through the question being really hyper alert of where these sums might turn up and how we'll use these results to aid the statistical techniques. Reading onwards, throughout the question we're going to pick n and k to always be integers. N's going to be bigger than 3, k's bigger than 2. Okay, and we're introducing a game, so it's going to be probably some kind of probabilistic game, and we're going to be wanting to know, if I do scan through to the end of part I, the probability of people winning. So in a game of k players, including Ada. So we've got a special character, of course, beginning with the letter A, but we have a total of k players, at least 2, are each given a random whole number from 1 to n. So for each player, each of these numbers is equally likely and assigned independently of all the others. So presumably that means they can also get a repeated value. All the numbers are equally likely and independent. If Ada gets the number 1, someone else could also get the number 1. A player wins the game if they are given a smaller number than all the other players. So there may be no winner. So we have a situation where all the numbers from we have our players, Ada, player 2, all the way up to player K, and they've each been given a secretive number. And the winner is going to be if whoever gets the smallest, providing that no other person gets that same smallest. So if 2 people get the number 1, there is no winner. Find an expression in terms of nk and a for the probability that Ada is given the number a and all the other players are given larger numbers. So we want the probability that Ada, I'm just going to say equals a bit of a loose definition of equals here, but Ada gets a and player 2 up to player K are all greater than a. Are given a number and all the other players are given larger numbers here. So in this case, Ada would win. She would win with the value of a because everyone else is larger. Well, the probability that Ada got exactly the value a is 1 over n. There were n possibilities for her to get. A is only one particular value. The probability that player 2 got a number larger, well, how many numbers are there larger than a? Well, that'll be n minus a. A good way to check is if, and I would write out a little bit of a number line here, if a was 1, then there's n minus 1. If a was 2, then there's n minus 2. And I hope you can see fairly obviously why that worked. But that was for player 2. But it could also have been true for player 3 and player 4, all the way up. So all the other players need to have a probability of n minus a over n to have that larger than a value. Okay, nice. Hence is probably my favourite word within mathematics. It's you've already done a lot of the hard work, go finish it off. Hence show that if k equals 4, so restricted now down to only 4 players. Oh, this should be k minus, because there are k players. We've already dealt with Ada, so we've got k minus 1 left to deal with. I was getting the numbers on the balls and the number of players mixed up. Sorry, hence show that if k equals 4, the probability that there is a winner in the game is that. Okay, well, let's first find the probability that Ada wins. Because if we can find the probability that Ada wins, and that's going to be the same, because everything's symmetric here, for the other 3 players, and then the probability of a winner is the total of those 4. So basically I can times this probability by 4 once I have it. Well, the probability that Ada wins is going to be, I kind of want to give this thing up here a name. I'm going to call this P of A. i.e. the probability that Ada wins with the value of A. So the probability Ada wins is going to be P of 1 plus P of 2 plus P of 3. Now, not P of 4. Oh no, that it could be up to P of 4. Yeah, plus all the way up to, again, I was getting the n's and the k's mixed up, P to n minus 1. So the probability that Ada wins is the probability she wins with a 1, or she won by rolling a 2, or rolling a 3. Now all these events are exclusive, mutually exclusive, they can't overlap, so we can just add them together to find the total. So this is, and I'm starting to see where this summation is going to come in. So P of 1, and I'm going to write this thing just subtly different. So it's going to be n minus 1 cubed, because the k is 4, over n to the 4, plus n minus 2 cubed over n to the 4, plus all the way down to n minus 1, all the way down to 1 cubed over n to the 4. Well, there's my summation. We're summing the cubes. Now we're summing them backwards. We started at the biggest, gone down to the smallest, but that doesn't stop us. So this is 1 over n to the 4, the sum from I equals 1 to n minus 1 of I cubed, which is 1 over n to the 4, quoting the formula at the top of the page, times a quarter. Now we're not going all the way up to n, we're going up to n minus 1, and then the n minus 1 plus 1 gives us an n squared, which is a quarter. The n minus 1 squared lives on the top, and cancelling with the n to the 4, we have an n squared on the denominator, which is almost what we have. But now the probability someone wins is going to be 4 times the probability that Ada wins by symmetry. There was no reason why we picked Ada out as a particularly special individual, so it could be any of them. Now if I do multiply that probability by 4, I get rid of the quarter, as stated in the question, getting the result as required. So that's part I. Okay, so presumably now we're going to build upon this game slightly further. And how exactly are we going to do that? One thing also to notice is we actually used the second result for this first part of the question. So now I'm actually expecting to use the sum of squares in this final section, which maybe, if you look down at what we're aiming for, could be slightly predictable. We've got an n plus 1. This looks like an n and an n plus 1. There's a squared on it, and where is that bracket gone? Maybe. Maybe not. Let's not speculate too far and actually attempt the question. So part 2. In a second game, K players, and now we've got 2 special people, Ada and Bob. They're each given a random whole number from 1 to n again. A player wins if they're given a smaller number than all the other players, or they're given a larger number than all the other players. So we're now picking out a winner if you are the smallest, like we had before, or if you're the largest. So there could actually be 2 winners in this game. So find an expression for the probability that Ada is given A and Bob is given A plus D plus 1. Okay, so Ada is given A, Bob is given some unpleasant combination A plus D plus 1, where D is a particular value to make sure things are in the range, and A is a particular value to keep things in the range. And all the other players are given numbers greater than A and less than that. So all the other players have been given things in this region. I'm now imagining a kind of a number line here, where Ada's at the bottom end of the number line, Bob's at the top end of the number line, everyone else is stuck in the middle. Hence we're going to then find a probability of exactly 2 winners. So let's try and find this probability. And again, I'm going to call this probably A, comma, there are now 2 inputs, A and D. I'm actually going to call it this. So that's going to be probability that Ada gets exactly A, Bob gets exactly A plus D plus 1, and all the other players, player 3 up to player K, are between those values, are in the set from A to A plus D plus 1. That's just shorthand notation for the inequality between the 2 values, excluding the endpoints. So how do I work this out? Well, the probability that Ada gets A is 1 over n. The probability that Bob gets A plus D plus 1 is 1 over n. They have to get those fixed given values. How many choices are there for the rest of the players? Again, I'm going to make some numbers up. If Ada got 3 and Bob got 7, so then this is 3 plus 3 plus 1. The D is 3. How many numbers are there in the middle? Well, it's exactly D. That's why Bob's number was chosen to be A plus D plus 1. So there are exactly D numbers in between. So there are D choices for all the other players out of n. And how many other players are there? There are K players, but we've already dealt with Bob and Ada. Do I want to simplify that in any way before I continue? Yeah, we might as well. So this is D to the K minus 2 over n to the K. Okay. Hence, show that if K equals 4, the probability that there are 2 winners in this game is that. So let's do like we did before. Let's have the probability, and now we need to be a bit more careful, because now we can have Ada being a small winner, Bob being a big winner, or the other way around, Bob being the small winner, Ada being the big winner. So I'm going to stick it this way round. So Ada, small win, Bob, big win. And then we're going to have to worry about how many combinations actually led to this. So the only way for this to happen with k equals 4 is there's actually quite a few different ways to get these a's and other values in there. I'm going to try writing it out first to start with, and then turn it into probably some summations. So this would be the probability that Ada gets 1, but Bob gets 3, plus the probability that Ada gets 1, Bob gets 4, plus all the way up to the probability that Ada gets 1 and Bob gets n. Those are all the possibilities of Ada winning when she picked 1 out. Or she could have picked 2 out. And then Bob would have to pick 4. Bob can't pick 3 because there's no space for all the other players to fit in between. Up to 2 to the n. Plus 3, 5. All the way up to 3n. And I'm particularly writing it in this way. And then the final one would be n minus 2 for Ada and n for Bob. So you've got this big, basically big triangle of possible combinations. And I'm keep going back in my mind to these conditions that the question gave us here. And they're actually giving us exactly the summations that's needed. These are all the possible values of A and Bob's value that give it all in. The D could be as large as n minus 2, so this thing is as large as n, which is indeed true, and A can go up to n minus 2 with D being 1. This is exactly the way that our summation is popping in. Now it's going to be a double summation because it's summing over the A's and summing over the D's. But if I actually look to my formula here, the sum of the A's, the summing over the A's doesn't make any difference. This was independent of the A's, which also makes sense. Nothing about this value mattered. The only thing that matters for this style of game is the distance between these values. Again, a really clever way for the question to have indexed the values. So this can be equal to the sum over, and the A can go from 1, and I should put this, get the summations the right way around, so I'm summing over D from 1 to n minus 2 of the sum of A going from 1 to n minus D minus 1 of D squared over n 4. Oh look, I'm summing over D squared. That seems to be, well, that is exactly what this question has kind of hinted at with the initial condition. So let's do these two summations. Let's do the inner summation first. We can't do the outer one first because there's a D within the inner summation. Now, how many terms are in that sum? Well, if I sum from 1 to 5, that's 5 terms. So it's just, I always have to do that check in my mind. Pick some random small values. So they're n minus D minus 1 terms of D squared over n to the 4. And now I'm summing over D, which is actually a lot more complex than it originally appears, because I've got really 3 summations going on here. So I can definitely factorize out the n to the 4. I'm actually going to put it as 2 different summations, not 3, depending on the type of D term that I have. So the n and the minus 1, I can factor out the n minus 1. That's going to be the sum of just D squared. And then we're subtracting the term here, which is 1 over n to the 4 sum of d equals 1 to n minus 2 of d cubed. So I've got my three terms, and I've simplified what exactly I'm summing over in each of those cases. So let's do the summations. N minus 1 over n to the 4 times the sum of d squared. So that's the sixth. So I'm going to put a 6 over here. The n, we're summing up to n minus 2. So n minus 2 is my n. N plus 1 becomes n minus 1. And then 2 lots of that plus 1 is a 2n minus 3. Not pleasant at all, but doable. Minus 1 over n to the 4, the sum of d cubed. So there's a quarter out in front. N minus 2 squared. And n minus 1 squared. So some things to notice already. I do have an n minus 2 and an n minus 1 that I'm expecting in here. But the rest of it is way more complex at the moment. So let's keep manipulating. I actually have my n minus 2, my n minus 1 squared, as I've got an extra n minus 1 up here. So let's factor out what I care about. I've got an n to the 4, n minus 2, n minus 1 squared. And I'm also going to factorize out a 12th. 12 being the lowest common multiple of the 6 and the 4. So my first term I've dealt with. I've got this term left, and I've got an extra factor of 2. So that's going to be 2 lots of that bracket. So that's 4n minus 6. Subtract. Now I've got an extra factor of 3. So that's 3 lots of the other term. And this is really pleasing because those n's have cancelled. So the minus 6 and the positive 6, those cancel. That leaves behind a 4n minus 3n. I'm going to do it slowly because officially it is a show that question. So therefore we're left with this, which is nearly what we want, except for that 12. So now let's consider, just like we did with this 4 here, let's consider how many different combinations of winners or ways to win there could be. So in a group of 4 people, well, there are 4 choices. There are 4 choices for a small winner, which previously was Ada. Small winner. Then 3 choices left for a big winner, which means there are 12 winner combos. So the probability of 2 winners is going to be 12 times the probability that Ada small, Bob big, which exactly cancels the 12 that we had that we didn't want. Oops, did not mean to undo that much. That's so quiet. Okay, nice. So we now have the probability of there being 2 winners in this adjusted game. In the final section, if k equals 4, what is the minimum value of n for which there are more likely to be exactly 2 winners than exactly 1 winner? Interesting. So we have the probability of having exactly 2 winners, but we don't yet have the probability of exactly 1 winner. that might mean we need to go back to part I slightly. And that might be more complex than one might originally think. So let's try and deal with the probability of having exactly one winner. So the probability of one winner, well, the winner could be a big winner or it could be a small winner. Now the probability of being a small winner is given in part I. Probability of being a big winner, is that not identical? We've got a symmetry between things being bigger and things being smaller. The issue is we might have an overlap. So let's kind of summarize what we have. So part I implies the probability of a small winner, which I should start abbreviating. That's quite a long phrase. We've written it enough times that we shouldn't really keep writing the same thing. I might just call that SW from now on. By symmetry, and we really like using this argument by symmetry, being a big winner. And let's make sure that we are convinced that this is fine. Having the smallest value does match exactly with being the biggest value. I could just rename all of these random number balls to be -1 up to -n, making a kind of a one-to-one matching. But now if you get -1, you're suddenly a big number, whereas before 1 was a small number. So it does match up beautifully. So the probability of being a big winner is n-1 squared over n squared. Now I can't just add these two together. Adding these two together would double count the middle section. And there's actually a rule for this. This is the addition law. States the probability of being a small winner or a big winner, which is what I want, to have exactly one. That's not exactly what I want, is it? I kind of want an excluded middle. So I don't really need the addition law, but the point of the addition law, it does come from a kind of Venn diagram-esque argument. So we have here small winner, big winner. We know the probability of small winner. We know the probability of big winner. And we know the probability of two winners, which is that middle section there, two winners. So we can work out the probability of exactly one winner by adding small and big, but then subtracting two lots of the double winner to kind of get rid of it. Okay, so let's do that. So probability of exactly one winner is going to be the probability of a small winner plus probability of a big winner minus two lots of the probability of two winners. So that's going to be, well, both of these are the same, so I can just say two lots of it. So this is two lots of n-1 squared over n squared minus two lots of n-2 n-1 squared over n cubed. Again, let's try and factorize what I can. I've got a 2, I've got an n-1 squared, I've got an n cubed, leaving behind an n on the first one minus an n-2. The n's cancel, leaving behind a plus 2. So that's going to be 4 lots of n-1 squared over n cubed. Okay, nice. So the probability of exactly one winner is given as that. So what did we want to do? What is the minimum value of n for which there's more likely to be exactly 2 than exactly 1? So we require the probability of 2 winners to be greater than the probability of 1 winner. Well, let's put that condition in. So n minus 2, n minus 1 squared over n cubed needs to be greater than this expression that I've just written down, n minus 1 squared over n cubed. This is just an inequality to solve. Particularly nice inequality because n is greater than or equal to 3, so nothing can be 0, and everything's going to therefore also be positive. So I can cancel a lot of stuff out. So the n minus 1 squareds can cancel, so n minus 2 needs to be greater than 4, and the n cubes on the denominator is also cancelled. So n is greater than 6, so the min value of n is 7. If n was to be equal to 6, then these two probabilities would be equal. So quite a large, actually, final part of the question for what felt like was just a quick comment on the end, but actually pulled in some nice other probabilistic techniques in there as well. As I've mentioned a couple of times, I was quite a big fan of these probability statistics style problems because they did turn out to be quite nicely algebraic once you got through the modelling probability section of there. Hopefully this playlist has been particularly helpful for you then. There'll probably be another one being made shortly for a step 3 paper. Until then, good luck with all your prep work.